right. I'm Craig Preston. I'm with CCL volunteer in Costa Mesa, California, and the California coordinator for the Conservative Caucus. But today I'm here to introduce our speaker today. Thank you. And thank you for being here for this early morning session. Today we are going to hear from Sandra, or Sandy, Kirtland Turner. As you can see up here, the science of past and future climate change. Sandy has a rich history here with CCL. Long ago, back when CCL started, long ago, 2006, is that right? 2007, she joined CCL, and she, it was one group? It was one group. She was in group number one. Her background, as you can see, she has some long titles up there: a paleoceanographer, a paleoclimatologist, and an Earth system modeler. Anybody know what those three things are? Oh, good. There are some people. You can explain it to me later. Her research focuses on reconstructing and modeling biogeochemistry and dynamics of the oceans during the early Cenozoic greenhouse world. Who knows when Cenozoic was? I looked it up. I Googled it. 33 to 65 million years ago. So we're going to hear about it.
We're in it still.
We're in it still. Oh, good. I'm going to learn today. So Sandy has volunteered with us since 2006, and she's also on the board of directors for Citizens Climate Education. So she has a rich history with us. Please join me in welcoming Sandy Turner.
Yes, I'm going to keep this with me, so hopefully I can move about a little bit more. So thank you, everyone, for joining me this morning. I want to give you the takeaway message at the beginning, which is that you hear a lot about the urgency of doing something about climate change, and that's absolutely true, but it's true for maybe two reasons. Excuse me. The first is probably, of course, that we want to avoid severe impacts on a timescale at which it's difficult for our societies to adapt. But the second is that what we're doing is something that will fundamentally change the climate system over civilizational timescales, not something that will change the climate for 100 years or 200 years, but thousands to tens of thousands of years. That's something that's often not really discussed, or it's perhaps underappreciated, and that's what I want to get into today. How we know that our current carbon dioxide pollution will affect the climate for that long into the future, and really some details about the implications of that. And so I come from looking at climate from the perspective of really long time scales. And so that's the basis of my talk, understanding how we know about climate change by looking at both the past and what that can tell us about the future. So of course, this is where we are today. I could have downloaded just a few days ago, the NASA Goddard Institute for Space Studies released their 2018 compilation or calculation of the global temperature change. So you're looking at anomalies. I don't have the scale bar really blown up at the top, but red is warmer, right? Blue is colder than the average from the middle of the last century. 2018 was the fourth warmest year on record. 2017 was the second warmest. 2016 was the warmest. So there's some variability and ups and downs, but we're in this persistent trend of extraordinarily warm temperatures, of course. And this is data that comes worldwide, more than 6,000 global stations. But I think another neat way to look at this is a graph that was just released by the National Oceanic and Atmospheric Administration, or NOAA, in the last few weeks. And this shows, in the context of 2018 temperatures, it's not just that we got overall warmer on a global basis, but that many places actually saw the record warmest temperatures. So even if we say 2018 was the fourth warmest year on record, if you look down around New Zealand, for instance, record warmest temperatures. Same with much of Central Europe. And so, what is the global mean is not necessarily the best way of looking at how extreme temperature changes in any given year for any given spot on the planet. But when we think about things in really long term, sometimes we like to look at them in one sort of simplified number, and that's where a global mean temperature comes into play, and it's really useful. And so here's another way of looking at our current temperature change and where we're at. So this is a temperature anomaly, or how warm or cold we are relative to some average period. In this case, that average period is taken from the latter half of the last century of 1960 to 1990. And then the line is showing you from, sort of the industrial era up until today, how temperature has changed on a global basis relative to that average period. And you can really nicely see the strong upward trend. And we are currently at not quite, but just about 1 degree Celsius warmer than the pre-industrial average in terms of our global mean temperature. So some of this, of course, is review for everyone in this room. But of course, this is due to increasing atmospheric carbon dioxide concentrations. So this shows on the top plot our graph of how the amount of carbon dioxide in the atmosphere has changed from the 1950s to today. And again, we couldn't measure this until the 1950s. So it was scientists just down the street from here at the Scripps Institution of Oceanography that worked out how we would measure atmospheric carbon dioxide concentrations. And they continue to do that work today in Mauna Loa, but also now many places around the world. And another crucial implication of that CO2 rise, which I'll talk about a lot, is that it's changing the nature of our ocean chemistry as well. So as CO2 goes up in the atmosphere, this blue line on the bottom shows that CO2 also goes up in the surface ocean because carbon dioxide dissolves very easily into the ocean surface. And when it does that, the green line shows that the pH, or a way that we measure the acidity of the oceans, decreases. So a lower pH number is a more acidic ocean. And those are numbers that we've actually only been compiling now for just a few decades. So we really want to put these things into context if we're trying to understand how this CO2 change will have implications for our ocean chemistry, for our temperature, very long into the future. We want more than a few decades worth of data. So we start using models, climate models, to try to tell us what will temperature change be, say by the end of the century. And this plot shows two ways of looking at what's going to happen, or what we project to happen by the year 2100. So on the top there is a very conservative estimate of changes in carbon dioxide emissions. And it's showing then how the amount of atmospheric carbon dioxide will change by the year 2100. And this is a scenario that the Intergovernmental Panel on Climate Change, or IPCC, has called their representative concentration pathway 2.6. That tells us about how much enhanced temperature forcing the globe sees as a consequence of our CO2. But built into that whole model is an idea that our emissions peak really in the next year or two, and then sharply decline afterwards, so that by the year 2100, there is no carbon dioxide emissions whatsoever. And you notice, of course, that we still get well above the concentration that we're at today. So today we're at about 400 parts per million on that y-axis. Those numbers go up to 500 on that scale, and we're peaking over 400 parts per million, well above that, even in this very conservative warming scenario. The bottom shows what that would mean for how temperature changes on a global basis. And you can see the colors are in the middle of this scale bar, and the oranges, that's the sort of 1 to 1.5 degrees Celsius change, which, as you might recall from last year, the IPCC had a report that came out discussing the implications of 1.5 degree temperature change, which are not negligible. There is still climate impacts that we're concerned about with this amount of change. But again, this is the conservative scenario. If we follow a business as usual pathway, the IPCC calls this the RCP 8.5. And what you're seeing in red is what atmospheric carbon dioxide does by the end of the century in that scenario. That's saying we continue to emit CO2, and we continue to increase our emissions of CO2 at the rate that we've been doing so for the last few decades. And now I've changed the axis. We're above 1,000 parts per million, so more than double what we are currently by the end of the century. And that all red graph is the consequences that climate models predict for the temperature change. So now look at those numbers. Those are globally more than 5, in some places up to 10 degrees Celsius of warming, compared to less than 1 so far. Okay, so what could we do? There's a lot of carbon out there, so I like to put it in perspectives of these nice little bar graphs. there are different units that we use to talk about how much CO2 we've released. Typically, people like me talk about just the carbon. So we say that currently we're burning carbon at a rate of 10 billion tons, that's the GT, of carbon per year. If you turn that into carbon dioxide, it's roughly 3 times that number because you have to take into account the oxygen and CO2. 10 billion tons per year. So far, if you add up all of our emissions of carbon since the start of the Industrial Revolution, that's about 300 billion tons that we've released to the atmosphere. If we continue on at even not the business as usual even, but kind of a modest assumption, we would easily surpass 1,000 billion tons of carbon emissions by 2100. And that bottom is our potential. That's how much a conservative estimate of fossil fuels are available. That's mostly coal, but about 5,000 billion tons. So there is a huge amount of carbon to tap into. And so the question is not whether we would run out before we could emit the sorts of amounts that we're discussing that would drive this major climate change. I also sometimes like to put this into context because I get a lot of questions about it. If you want to think about how much carbon we're actually putting into the atmosphere per year, that's about 100 times the amount of carbon dioxide released by volcanoes. So we are massively, massively overwhelming natural sources of carbon dioxide to the atmosphere. Okay, so but I said I really want to think about the long time scale because you might wonder, well, what happens to us after the year 2100? At the end of those graphs on the previous slide, if we follow business as usual, we're in this upward trajectory. That's only maybe, in the worst case scenario, having burned 1/5 of the available carbon that we could emit. And so let's try to think about the amount of time over which we'd want to know the impacts of that CO2. So I like to start by going backwards. And I'm going to take a time scale of civilization, which I think for that, 10,000 years is a nice number. So where were we 10,000 years ago? This graph is showing for the last 32,000 years, we're moving from the present over here and then back in time this way. And this is showing changes in sea level. I've got the little red bars kind of giving you indications of, the time scale of civilization. Written history for maybe the last 5,000 years. The rise of civilization, perhaps about 10,000 years ago. And you can see that there's this massive change happening in sea level. At about 20,000 years ago, we were in an ice age. And then, interestingly, we see sort of the rise of civilization as the sea level rise from the melting of the ice sheets during the last ice age are kind of tailing out. And if we go back, we can use methods to try to reconstruct how was atmospheric CO2 changing on these timescales and maybe other greenhouse gases. And so we do that by looking at the Greenland ice sheet. And these 3 plots are now showing for the last 11,000 years, same thing, starting at present and moving back, how some of these important greenhouse gases were changing in the atmosphere. Carbon dioxide is on the top in green. In the middle, we have methane, which is another important greenhouse gas. And on the bottom, we have nitrous oxide, another important greenhouse gas. And if you focus on the present, you can see kind of pasted on there the sharp upward swing from what we're doing today. But you notice that otherwise, things are pretty stable during this long interval in which we had the rise of all of our civilization. You don't have much change from a value of carbon dioxide of, around 270 parts per million of carbon dioxide in the atmosphere. And so what that tells us is correlation or causation. Humanity as we know it, civilization as we know it, arose in a period of quiescence or stability in atmospheric CO2 at a time when we were coming out of a last ice age and things had begun to stabilize, sea level wasn't changing rapidly, temperature wasn't changing rapidly. I look at that and think, well, climate stability is clearly important, not just for today, but for our civilization as we know it. Okay, but we want to know something about, well, how does the Earth respond to big changes? So maybe we can go even further back in time if the last 10,000 years of humanity's history were very quiet in terms of climate change. Well, if we go back further, we look at a series of ice ages. So this is on the top here. Now, I'm sorry for switching around. Paleoclimatologists are used to, we do this all the time. We switch our timescales back and forth. But this is now from the present, moving back, that's 1 million years ago, or 1,000 years into the past. And on the top, that's how atmospheric carbon dioxide has changed from ice core measurements. And on the bottom, it's an estimate of changes in temperature by looking at little fossil shells of organisms that live on the seafloor. And if you notice the scale bar, we never went above 300 parts per million CO2 in the atmosphere for the last 1 million years. And that's known from directly measuring the CO2 trapped in little bubbles of air that are formed in ice. And going along with those changes in CO2, though, we see how important carbon dioxide is for global temperature. When CO2 is lower, we are colder, the kind of blue shading on that bottom plot. When CO2 is higher, we're warmer. But that's not telling us anything about the possible futures of having much higher CO2, or even CO2 at the levels that we are right at this very moment. And moreover, those changes, in case anyone were to ask, are very predictable things. We understand why we have these cyclical changes in ice sheets, and they're based on ways that the Earth changes in its orbit as it moves around the sun, all very well known but relatively slow processes. What those ice ages do tell us, however, is that carbon dioxide moves quite dynamically in the Earth system. It goes from the oceans, where most of our carbon is stored, into the atmosphere, into the biosphere, or plants and soil. And there is no inherent reason that the CO2 must be stable. So most of the carbon, the vast majority, I drew this actually to scale, is in the oceans. And we actually know now, through decades of study, that the reason CO2 changed across the ice ages was because it was coming in and out of the oceans. Well, this is important, one, because it gives us some ability to tell how changes in carbon dioxide affect temperature and climate, but it also tells us that we're messing with a sensitive system. It's not just a question of how much carbon we directly choose to emit or burn by burning fossil fuels, but we don't want to change this balance. And we can, because we know the planet can do that. It can take carbon that's in the ocean and it can put it into the atmosphere. So that's where we get concerned. But still, we don't have an analog for what's happening today. It turns out, if we want to understand climate change in a time of global warmth or CO2 levels that are approaching values that we currently experience or might experience in the coming centuries, we have to go very, very far back in time. And really the only way to do this is by looking at the record of climate preserved in deep ocean sediments. This is one of the things that I do in my lab. So we go out to sea, we drill into the seafloor, we obtain these little fossils that are shown on the bottom, tiny little microscopic things. We burn up their shells. This is in my lab. We measure aspects of their chemical composition. It allows us to reconstruct aspects of climate in the past. This is a huge wealth of information, but this is what studies like that have told us about the evolution of our climate now over the last 65 million years of Earth history. Why the sudden change in timescale? Well, you have to go back a very, very, very long time ago before you see anything like the atmospheric CO2 we might expect by just less than 100 years in the future. So this is the present, 0 over here, 65 million years ago in the past. On the very top is a measurement of global temperature. And all you need to know here is that there's a trend from hot to cold. This middle bit tells us a bit of information about how carbon moves through the Earth system. It's telling us about transfers of carbon, for instance, from the oceans and into the atmosphere. And this bottom plot is a bunch of ways that we estimate atmospheric CO2 change. The ice core record only extends 1 million years into the past, and so we have to go much further back than that with other kinds of methods for estimating CO2. But if you look at the scale bar here, 1,000 parts per million, which is what I showed us kind of reaching by the year 2100, we're tens of millions of years ago before we see those kinds of values. And so those are the timescales that we have to work on if we want to understand the implications of that sort of amount of CO2. Moreover, it turns out that we can go into the deep sea sediments and we find evidence for very rapid changes in the amount of carbon dioxide that were stored in the oceans and atmosphere system A really brief overview is a famous event that scientists like me study to understand the timescale of CO2 change is something called the Paleocene-Eocene thermal maximum. This is a picture of a sediment core in which we recognize these things. I'm not going to talk too much about the data types, but again, it comes from these microfossils on the seafloor. And we can basically use a measurement that we call the carbon isotopes in these things to tell us that atmospheric CO2 changed. So this is a zoom in of this core, and we see this sudden change in a variable that this is from a model. As we see a change in the variable we can actually measure in black, it indicates that atmospheric CO2 peaks. And we can actually work out something by how high atmospheric CO2 got. So we think, based on a range of evidence, that we went from something like just shy of 1,000 parts per million to 3,000 parts per million during this event in the past. And we can also reconstruct impacts like changes in temperature. This event was associated with about 7 degrees Celsius global warming. Another important thing I want to point out here, and I'll zoom in on this is a model of this event. That's 25,000 years at which CO2 remained high based on our data. We even see things like evidence for ocean acidification. It turns out that the kind of sediments you get on the seafloor are closely tied to the acidity of the oceans or the ocean's pH. And we see things like this all over the place across this event, where in the bottom you start out with these nice white chalky sediments, and then right at the time that we can deduce there was a big change in CO2 and temperature, you dissolve all of that chalk, it turns brown to clay, and then slowly recovers. We can use this timeline to tell us how long does the CO2 that was emitted stay in the system and continue to cause effects on climate and ocean chemistry. Yeah? Calcium carbonate, yeah, buffers carbon dioxide change in the atmosphere. And I can go into details about that if you'd like later. So when we use the kind of information that we get from studying these past events to build our models of the climate and carbon cycle, we can do things like this. Now I'm showing data on this side of the Paleocene-Eocene thermal maximum. This weight percent is what that stands for. Amount of carbonate in the sediments shows that ocean acidification effect, the drop in carbonate. This value on this side is telling us a little bit about how changes in CO2 happen. It's an indirect estimate of that. And we can try to create models of what sediments on the seafloor will look like into the future because of our emissions of CO2 today. And that's what I'm showing here in 2 different lines, where I say if we just assume that our historical emissions, so up to the year 2010 in this model, are all that we emitted, what would that look like preserved on the seafloor 100,000 years into the future? Or if we take kind of a mid-range scenario of emissions in the red line, what would that look like? And there's similarities is the basic idea here. So we see the same kind of features in the future based on what we would expect to see from, or based on what we see from the PETM. So this becomes a really nice comparable episode for understanding climate change. And we can build all of that understanding into models that we build in order to look at the very, very long-term impacts of CO2 pollution. So if this is the result that I showed you before of how carbon dioxide evolves by the end of our century, now I've included a range of different scenarios that the IPCC utilizes. So this is just their terminology. These RCP scenarios, again, stand for representative concentration pathways. Those numbers have to do with the enhanced warming effect due to the amount of CO2 into the atmosphere. And basically, these are incorporating a bunch of different assumptions about economic activity and legal choices. So this blue curve is the lower of the 2 scenarios I showed earlier. And again, the assumption built in there is that emissions peak within really the next few years. So when these were released, they said emissions peak by 2020 and then begin sharply declining thereafter. The green is emissions peaking by 2040, and the orange is emissions peaking by the end of the century, and the red is that emissions are continuing to rise at the end of the century. That would be the business as usual scenario. Okay, so those aren't scientific scenarios in a sense, they're socioeconomic scenarios, but we can think about what they mean by incorporating them into a model to tell us how CO2 would increase as a result. But we can now, with our understanding of how the carbon cycle works, based on our knowledge of the past, run this model much further into the future and ask how these various things make CO2 evolve hundreds, thousands of years hence. And this is what we get. I've run this out this is a model run for 10,000 years into the future. So it's just a continuation of each of those lines. And again, now look at the scale. You're 2,000 parts per million in the next few hundred years from the RCP 8.5 scenario. And even if you look at the very end of this experiment, 10,000 years hence, you're still above 1,000 parts per million atmospheric CO2 in the scenario in which we continued on with business as usual till the end of this century. So that is a way in which the actions of this century directly translate to changes 10,000 years from now, double our civilizational timescale thus far. Yeah.
And in your simulation, the loss of CO2 from the atmosphere is driven solely by geological weather.
Natural processes. Ocean uptake of that carbon dioxide is the fastest effect on this time scale. We actually have to go much, much longer before weathering kicks in a substantial way. Yeah.
I heard that the maximum CO2 that could happen would be about the CO2 that was in the time of the dinosaurs, that release from the... That's what I heard. I don't know.
Yeah, no, that's... Oh, so the question was about a maximum CO2 that can be achieved. There isn't really a theoretical maximum. You can go back further in time than that, where CO2 actually becomes a significant constituent of our atmosphere. In early Earth history, it was in the percentage range, whereas now it's in the hundreds of parts per million range. We think about the maximum based on if we took all of that easily accessible fossil fuel reservoir, that 5,000 billion tons, and burned that. What would that give us? That is higher than these values. Because this red line is still only in total burning, that's about 2/3 of that maximum. So we could get higher than this theoretically based on accessing those CO2 reserves, but that isn't to say that there isn't more carbon out there that could eventually make it into the atmosphere. It's just not obvious how humans would do it. So that might be the kind of thing you're hearing about, what people say is theoretically possible based on what we could access and burn. You could start burning up sedimentary rocks, which is where most of our carbon is on the surface of the Earth, and CO2 would get much, much higher than these numbers. This is potential based on human, logical human behavior, I suppose, doing it for energy. That's why I sort of chuckling. Should I come back to these? Finish one or two more. I think we're still doing okay on time, because I want to show you how this translates into an impact on climate in this model. This is how mean atmospheric temperature changes in all of these scenarios, 10,000 years into the future. And so again, remember we talked about how this is a very conservative model. We're peaking at only about 8 degrees warming, but what I really want you to focus on is the persistence of that temperature change in 10,000 years from now. We still have more than 5 degrees about Celsius warming in the scenario in which we follow business as usual emissions to the end of this century. And so another way of thinking about that is that we will have seen the climate change that we're so concerned about seeing at the year 2100 for another 10,000 years if we don't begin to lower our emissions of carbon before the year 2100. Ice sheet modelers. A lot of people are the most concerned about sea level rise as far as climate change impacts go. That could be a personal debate, but I hear a lot of questions about that one. And there is a lot of uncertainty in terms of how much sea level will rise by the end of this century. Understanding the stability of ice sheets is not a simple process. However, it is pretty simple to say that in 10,000 years, if global temperature was 5 degrees warmer than pre-industrial for that entire time, we know definitively that that's enough to melt all the ice sheets. So even if I'm not saying that you melt them by 2100, I'm absolutely not saying that, 10,000 years from now, you could have a world that has no ice sheets. And I think to think about how fundamentally that would mean that our generations have changed the planet for the timescales on which our civilizations have currently existed is a different and very profound way of thinking about climate change than just thinking about the timescales of our children or our grandchildren. We're talking about how do we look at the ancient Romans? How would people in the future look at us for what we've done to the planet now? So that is all I have to show, and I'm happy since I know there were a number of questions. We have 5 minutes left for questions. Thanks. So I'll go here first.
Yes, the red line that extends out
Yeah.
10,000 years declines. What assumptions underlie that decline of the red line?
Yeah, so this is so in order to run these kinds of simulations on this time scale, this is a less complicated model than the IPCC uses. So we kind of inherit a climate sensitivity from those models, and that means how much temperature change we get per change in CO2 in the atmosphere. So this number really comes from how much CO2 is left in the atmosphere at the end of this simulation. And what someone before asked that I alluded to is that the amount of CO2 that's still in the atmosphere on that time scale is after accounting for how much can be dissolved into the oceans over those time scales. And there are a bunch of different things that control that, the temperature of the oceans, but also aspects of the ocean chemistry. And so this model, what it's really good at doing is saying very, very precisely how much CO2 there is. And then we kind of take a more sophisticated model's basis of turning that into changes in temperature. So this model is conservative in terms of its climate sensitivity. We have around 3 degrees Celsius each time you double atmospheric CO2. There are other models that suggest there's more warming than that, which would push these up in an absolute sense in terms of temperature change. But this model, its specialty is how much CO2 is in the atmosphere. Yeah. Yeah, exactly. It's enhanced radiative forcing by the end of the century. Yeah, in the back. That's an excellent question. So, yeah, sorry. The question was, because we're now on these long time scales, how does this interplay with the glacial cycles? And so the simple answer for those is that just like all natural climate variability, it kind of continues in the background, but it's sort of swamped by the anthropogenic or human influence. So if you think about the fact that over, say, the last 1,000,000 years, we've been going in and out of ice ages every about 100,000 years. So our last ice age hit its maximum 20,000 years ago. And we know that it takes a much longer time to go into an ice age than it does to come out. And so if we wanted to just say we were doing a parallel to the last few glacial cycles, we'd shortly begin to steadily, very, very slowly, over tens of thousands of years, go into another ice age. Everyone who works on this says we wouldn't, because what we've already done in terms of enhanced radiative forcing is larger than the changes that we get in the orbit of the Earth on those timescales, and so we won't see the same kind of behavior of the climate system as a result. We can run simulations, though, where we include those changes in Earth's orbit, and we include the effects that would have on how much energy we get from the sun, along with all of these kinds of different CO2 emissions trajectories, and they move them around a little bit, but we're talking about slight wiggles. These patterns are still what dominate the climate system. Yeah. Yeah. That's a model. We have data that has big error bars, but probably we were starting out at higher CO2 than today, so we think close to 1,000 parts per million, and again, there's error on that. So that particular event was about 56 million years ago. Yeah. Yeah, so one for time, but also because those are actually things that are still actively debated by our community, our research community. So we debate how fast, and we debate exactly how much carbon and exactly how high CO2 got. This is something that I've contributed to the discussion of a lot. I fall in the camp that the carbon sort of went into the atmosphere over a few thousand years, which means that the rates were still like 10 times slower in terms of CO2 release during that event compared to today. So that event is still an underestimate of what we could do now. Yeah, and then in terms of the amount of carbon, I think that scenario is pretty reasonable, where you probably raised atmospheric CO2 by something like 2,000 parts per million. So it was, I had a colleague who wrote a really neat little paper recently that was trying to put it in context and said that if we continue at our current rate of emissions growth now, we will have created another PETM, which is our abbreviation for that event, in 400 years. So that kind of contextualizes, even though that event was enormous and happened slower, we could compress the same amount of carbon release into a much shorter time scale today. Oh, yeah, sorry, I missed that one. And the source of CO2, again, is also debated. There was a lot of volcanism at the time because there was tectonic changes going on in the North Atlantic. That's one hypothesis. Another hypothesis has to do with feedbacks, because this was in a longer-term interval of warming that related to the melting of methane hydrates stored on the seafloor. Which concerns a lot of people because we have methane hydrates on the seafloor today that can melt as a result of ocean warming. And so again, those are really, really debated things in the scientific community. Are we at? Okay, one last question. Sure. So the question, just to repeat it, was how important are our agricultural practices in these CO2 emissions? And I would say, though I'm not an expert on that sort of land use change aspect, I mean, I would say it's net carbon emissions that we care about. So wherever it comes from, whether it comes from changes in land use or changes in fossil fuel emissions, almost doesn't matter for these purposes. Personally, I think we should, and it's important. No-till agriculture, for instance, is known to really help preserve the carbon stored in the soils. In general, though, I think for dealing with the sequestering or removing from the atmosphere the really large volumes we've put in, we need to look at reservoirs of carbon that are much more deeply protected. The problem with soil carbon is from the carbon cycle modeler perspective, we would say that that's still in a very readily exchangeable pool with the atmosphere. And if we want to get things out, and so that they couldn't, for instance, natural changes in climate will change how much carbon is naturally stored in soils. We don't want that carbon to then exchange, so we'd have to think about locking it deeper down. People talk about deep ocean carbon storage or, deep underground reservoirs. But I still think that changes in land use and agriculture are absolutely an important part of getting those emissions down soon. So, yeah.